Hi, everyone.
Hi. Why don't we introduce Jeff? Jeff, thank you for giving the talk. So Jeff is a first-year PhD student who graduated from ETH Zurich before and is working with Lakshman and David Harris. He'll speak about his work with Andreas Karrenbauer on online fractional knapsack. Go ahead, please.
Thank you very much, Arvind. Hi, everyone. Thanks a lot for being here. Excited to give this talk. So let's dive in. I'll start outlining the problem both in the offline and online setting. Then we'll see two algorithms, a knapsack algorithm and a secretary algorithm. We'll use both of them and merge these two in maybe in an unusual manner to obtain the algorithm that achieves the final competitive ratio. And then we'll discuss some potential future directions. One reason I'm giving the talk is that I do believe there is some room for improvement. And it's a cute, simple algorithm, the one that we will see. So you may already know the fractional knapsack. Let's just recall it. So there are n items, each with a value denoted by vi in red, and a size si in blue. There is a knapsack whose capacity is w. Without loss of generality, we can normalize the weights, so the knapsack capacity is assumed to be 1. There is a well-known algorithm to solve this problem. So, okay, the goal is to find out maximum profit packing. So you will set the variables xi that are the fraction of each item in the final packing. So we subject to the packing constraint. You want to find a packing that maximizes the profit. There is a well-known greedy algorithm to do this. So we sort the items from the highest profit to weight ratio to the lowest, and then we simply go through them. And as long as there is knapsack capacity available, we pack the items. So consider the first item. Its profit to weight ratio is 2.5. It's the highest one. There is enough knapsack capacity, so we pick it integrally. Its xi is set to 1. For the second item, there is still knapsack capacity, so also that one will be set to 1. We come to the third one, and it's larger than the available capacity, so we pick it up to a 0.75 fraction. For the remaining items, their xi's are 0. This solution is optimal, as you can see, and its profit is 2.05. This problem in the offline setting is this simple. Let's move on to the online version. In the online version, we consider random arrivals. So an adversary can decide the value and the size of the items, but a permutation drawn uniformly at random decides the order of the items. So the algorithm will see item one by one, decide immediately, and irrevocably the xi's, so the fraction of the item in the final packing. We denote by W prime the remaining knapsack capacity, and V denotes the current profit, big capital V. So maybe those who haven't seen this kind of problems, do you have some ideas? What are the usual approach, how to go about these problems? For example, when you don't know anything about the instance and you need to start, what are possible ways? Right, that makes sense. It's maybe even too generous, so we just reject the first items. With some probability, these items are not important because the permutation is randomly. So say the first two are rejected. Sometimes they can be good, sometimes bad. Like it's just average, I guess, average case. So, but the good thing is that now we have seen some items. We have some idea of what the instance looks like. And as we go through items, the intermediate solutions gets closer to the final one. So at the end, we'll of course see the optimal solution. But at this point, we just see some intermediate solution. And based on that, we can decide whether to pack the next item or not. So consider this item as a profit to weight ratio 2.5, which is higher than those seen before. So we could think it's a good item. Let's take it. The next one, 1.25. It's maybe not so good compared to the one before and also the first one. So we pick, say, half. We don't want to fill up the knapsack too early. Then it happens that the last one is pretty good and we fill up the knapsack. At the end, our current profit is 1.825. This is just 1.12 factor away from the optimum. In this instance, we say that this is 1.12 competitive algorithm. In general, this is too good to hope for. We'll not get that constant. But before moving on to like how we characterize the competitive ratio, are there any questions? Is the problem setting clear? Good. Okay, we say that an algorithm is R competitive when it achieves a 1 over R or like R approximation. I have seen both notations, and possibly there is a little O of 1 that vanishes asymptotically as growing N. Opt I is, of course, the optimal offline solution, and the expectation is taken over all input random permutations and all the random choices of the algorithm, if any. Okay, with this notion in mind, let me tell you about previous work. So the first kind of problem similar to the one I'm talking today about is the secretary problem. We'll see towards the end. I won't define it now. There is an e-competitive algorithm that was developed by Dinkin that is optimal. This comes from optimal stopping theory, which maybe is some separate field. Then Marchettis, Paccamela, and Vercelli started looking at the online knapsack and showed that there is no constant competitive algorithm when items arrive in an adversarial manner. This motivates this beyond worst case assumption that you get a random permutation rather than an adversarial order. So Babayov et al. Initiated the study of the integral version in the online setting, showing an e-competitive algorithm that resembles the one we are going to see. Then Castellan showed 8.06 using primal dual framework. Finally, Albers and Ladewig, which I will refer to as AKL, gave a 6.65 competitive algorithm for the integral version. Karrenbauer and Kovalevskaya showed that if you use AKL algorithm as a black box, you get a 9.37. And in this work, we open up AKL algorithm and build upon it to get a 4.39. So this is the result of the paper, 4.39 competitive deterministic algorithm for the line fractional knapsack problem as defined earlier in the random order model. So now let me overview a little bit the ideas, the approach that we will take. This, I tell you, might be a bit disappointing because there are no Chernoff-Hofting bounds, there is no rounding, and there is no duality. But there is an application of Markov's inequality. So in some sense, we will see very simple tools. Nevertheless, they do quite a good job. So the constant competitive ratio, it's not always possible to aim for something constant. So this problem admits a relatively good competitive ratio, and the best lower bound is the E. Okay, so we take AKL algorithm, and we show that if you consider also the ability to pack items fractionally, you can improve the competitive ratio. Well, we will change at the end to show this competitive ratio. We will have a bit to change from their paper and average over all item profits. In some sense, there will be some items that you can do better on those. So we will redistribute some excess to all the items to get the final competitive ratio. Okay, this is the high-level picture. And we'll start with the knapsack algorithm. By the way, it might be a little bit shorter than an hour, so maybe 35 minutes or so the overall. Okay, knapsack algorithm. Let me just. Good. As I anticipated before, the high-level idea is that we have a sampling phase where we reject all items. Then in the AK, in the green phase, we will pack items. At each round, we compute an intermediate solution with the items seen so far and use that to decide the fraction of that item in the final packing. Sorry. More formally, we have a parameter D that decides when the algorithm starts swapping items. Our output are the xi's. We denote by L the current round, I the current item. So in the packing phase, we compute the intermediate solution on the first L items, and we set xi to be either the current solution, if there is enough capacity, or the maximum possible fraction allowed by the remaining knapsack capacity. Any question on the algorithm? W prime is the remaining knapsack capacity. If that is enough, then we pack according to xi superscript L. Otherwise, we just take the maximum possible fraction to fill up the knapsack. This xl can be computed using the greedy algorithm, for example, ordering items by profit to weight ratio, or solving an LP, whichever available. Okay, if the algorithm is clear, we proceed to the analysis. Okay, the analysis consists of a few steps. The first thing we want to do is to model the expected consumed capacity. So at around L, how much capacity do we expect to have? We model the random process as follows. Let X be the capacity used by algorithm K up to this point, and consider each round individually. So Xk is the capacity that we are going to use at round K, and Qk is the random K item subset that we have seen up to that point. So we enjoy linearity of expectation and think of each round as an independent random experiment. This is something that also other papers do, and it's pretty nice because then you can consider only this current round and its resource consumption according to some K item subset. For a fixed item of this subset, we consider the probability item J is revealed at round K. Then what we do is to pack item J according to fraction Xj. So Xj times Xj is what our algorithm will consume in terms of resources in the knapsack. 1 over K is the probability item J at round K. Then we saw that Xj can be said to be at most the solution on these first K items. And regardless of Qk, we know that this is a knapsack solution. So the sum of these items is at most W. And we use this fact to get this extraction that sum up over K leads to W times log L, that is the current round over the N. So now we know at round L how much capacity we are expected to consume, and we want to say if there is enough capacity, then we can pack an item up to some X fraction. Yeah, say X fraction of item I, which will take Si times X space. So now consider if there is more space available, that's fine. It will be just bigger. So we are consider, okay, is there enough at least X times Xi space remaining in a knapsack in expectation? So consider around L, where item I will be revealed. And we sum over all L rounds from throughout the packing phase. So now X was our resource consumption. If the resource consumption is less than 1 minus, this delta is the fraction of the knapsack that we need to pack this item. Then we take the complement so that we can apply Markovs. So 1 minus the probability that we are using more than 1 minus delta W capacity. And we get the expectation we computed before over 1 minus delta W. And then we can actually sum this up and obtain a closed formula that is that quantity there. Any question up to this point? So essentially, we bounded the expected consumption, and using that expectation, we could show that with some probability, we can pack this X fraction of item I. Why this is still, say, not enough? Now we know how to compute this probability, xi. So xi is a random variable denoting the quantity, the fraction of item I that we put into the knapsack. We know how to compute is at least x, but this is maybe not that good as a lower bound on the expected profit that algorithm AK gets from item I, right? Because xi star is the fraction of item I in the optimal offline solution. So if you think about it, you could pack item I for any fraction between 0 and xi star. So now the idea is to use the probability on greater or equal x to sort of approximate the probability distribution. I'll guide you through this calculation. The idea is pretty simple. So you think of the interval 0 xi star as many small intervals, each one of length 1 over n, where this n is chosen arbitrarily large. So you have all these many small intervals, and you use your lower bound on xi greater or equal x as the probability of that small interval. So getting to the math. This term is just, okay, suppose this is greater or equal than xi star, that case is fine. Instead, if we are in this case, it's a bit more complicated. So this xi equal x, we don't know, but we consider these as small intervals. And if the xi is between xj and xj plus 1, xj is definitely smaller than xj plus 1, so it's kind of a lower bound. But as these two are arbitrarily close, we don't lose too much. Then, simply probability. This is intervals, this probability is like exactly the same as xi greater or equal xj minus xi greater or equal xj plus 1. Now, this looks already a bit better than before, still not quite, because the first term has something positive is in front, so we can use the lower bound. The other term is negative, so we cannot apply the lower bound. But we can rearrange the summation because this xj plus 1 will have in front xj plus 1, or if you consider xj, then xj plus 1 appeared in the summation before. So if you rearrange, you get xj minus 1 times the probability that we know how to compute. Then this difference is 1 over n, and we can plug in the quantity from before there. And actually, when you do this, you can lower bound all this sum in a closed formula. it's a bit long, the expression, so I'll show you graphically. Even if I know, like, all the calculations, even if one got lost, essentially we could lower bound this area to the blue one and the red one, and then their difference gave us a lower bound on the on that range where xi could lay between xj and xj plus 1. And then what this quantity evaluates to as this q function of mu I, where mu I is the utilization of the knapsack in the offline solution. So item I in the offline solution has utilization Si xi star divided by W. And as you see, if an item, say, is as large as the knapsack, so 1, it's packed for 0.15. Yeah, this is not 0, it's about 0.15. And if an item is almost 0, actually it can be packed with probability about 0.29. And this will be the main ingredient to achieve the competitive ratio mentioned before. This is all the knapsack algorithm. Any question? Good. Let's move on to the secretary algorithm. So anyone who doesn't know the secretary algorithm, and they can pick on for some questions, like you already know secretary algorithm? No? Okay, good. So we saw before, the first step is rejecting items, because that way we cannot be too wrong when we make decisions. We already know part of the instance. Then the idea is to take the item that has a profit higher than the highest seen in the sampling phase. So we name best sample the item with the highest profit in the sampling phase. Any item higher than that in terms of profit will be packed up to the maximum possible fraction.
Excuse me, Jeff.
Yes.
I'm sorry that I have to drop off now for my next meeting, but enjoy your talk, and then maybe you and I can talk later about your paper.
Perfect. Thanks very much.
Okay, thanks. Thanks. Bye.
Bye. This start, the maximum profit up around the packing phase, sampling phase, CN. If an item in the later phase is higher than this star, okay, let's pack it up to the possible fraction without computing any fractional knapsack. As simple as that. How much profit can we get from packing the most profitable item? The proof is more combinatorics, more counting. And we model it as follows. So think of the most profitable item being at a position K that is in the packing phase between Cn plus 1 and N. Second, the best sample is some item that has rank greater than our most profitable item, say A. This A is at least 2, but it can be also 3, 4. The thing is that if the best sample has rank A, no item with a lower rank can end up between A, or actually from the beginning up to position K. Because otherwise, it will either our best sample would not be the best, or we would pack this other item that has lower rank. Okay, this actually can be seen as balls into bins, where you have n-2 items, -2 because we have taken away the most profitable item and the best sample. So we have those n-2 items, out of which n-a are kind of good ones that we can pick. Instead, the others are kind of bad, would ruin our chances of packing the most profitable item. And then this is just counting. So 1/n is the probability our most profitable item is at position K. The best sample can be at any position between 1 and Cn. So we have got Cn over n-1, n-1 because we have fixed the position of the most profitable item. And then this ball into bins game where only n-a are good, and we need to draw k-2 balls, is actually modeled as this ratio of binomial coefficients. And I'm omitting the calculation, but actually you can get a closed formula. Like this n-2, k-2 is actually independent of a, so you can pull it out. Then this with the sum can be obtained written nicely enough that some terms cancel, and then with this other summation you can get to show that it's E. Since we consider the most profitable item, there is no item that is like better than that. Therefore, this is at least bi xi star, where that is the value of any item in the solution. Xi star is the optimal offline solution. Good. This is all the secretary algorithm. Any question? Is it clear? Good. With this, now we combine the two of them. So if you've seen already this kind of item, this kind of problems, the most natural approach is to toss a coin and then you optimize the probability of this coin coming up head or tail, and you run either a yes or AK with that probability. And I'm showing you that there is another approach that does better. So, okay, random choice most of the time works, but sometimes the one maybe can do better. This is one of the case. This was already shown in AKL, so it's not from our paper. It's interesting and can be applied here as well. So if in this secretary problem, if there is no item larger than the best sample, you will not pack anything. So with probability C over D, this is the case. The best sample is kind of better than anything after. So we enjoy this to say that with probability C over D, AK can kind of start after the secretary algorithm with an empty knapsack. So this quite nice sequential approach is possible because with some probability that is constant, this AS is not packing anything. And yet we can then merge the contribution from both algorithms. Okay, let's try to do that. This is how then the algorithm looks like. You can actually parameterize and show that if you run AS for Cn to Dn, you get less than E, of course, but still something that is a function of D. And naturally for AK, you start from Dn with an empty knapsack with probability C over D. So you just multiply the expected profit by C over D. Good. So this is the profit of the algorithm. There are two free parameters that are C and D. How we optimize them? So consider, we will show that then this works, but just to upper bound, to say it cannot do better than that, we have the one item case and the many item case. Suppose the optimal applying solution is just one item. There is just one item, okay? the secretary algorithm gives you this P1, and then the other phase, the knapsack algorithm will give you this quantity with utilization 1, so Q of 1. And this is the maximum we can get from this algorithm. On the other hand, suppose the solution contains very large number of items, all of which have very low utilization. All of them are very small, then you cannot get better than C over D times Q of 0. Okay, and now we solve the optimization problem. You can rearrange the quantities and show that everything can be expressed as a function of D, that is, and the Z is maximized for 0.6 D, and C that is about 0.47. And Z is eventually our competitive ratio. Okay, now we show that that is actually what you can get. The proof goes as follows. So without loss of generality, we label items in descending order of contribution. So if an item has less contribution, we can also say that it's probably lighter. So also, the larger the contribution, the larger the weight. Otherwise, the expected profit will only be better. We make this to one label items and say the utilization are in descending order. Then we know for all items except the first one, this holds. Only the first one can get more profit because the first item, the most profitable one, its profit comes from the secretary algorithm that gives P1 and from the knapsack that gives this other term. Otherwise, everything is less than Z. And what we say is if the first item gets more than Z, then we give its success to other items. Since this first item is the most profitable, this it should be 1. Sorry, it's not J, it's B1 X1 star. Then this is larger than any other item. So we take a bit from its probability and give it to other items. So then the cardinality of opt times C should be at least this. So this one should be at least that. And with some calculations, actually, you can show that their difference. So if you bring Z times cardinality of opt from the other side, and one plugs in value, can show that the quantity is positive. So actually, the competitive ratio is obtained. You also see that the left-hand side is actually, of course, the utilization sum up to 1, and it's minimized when mu1 tends to 1 and mu_j tends to 0. Good. And this is the final analysis. Any questions? Okay, some future directions that I find interesting. We saw the 4.39 competitive ratio is achieved by the combination of knapsack algorithm, secretary algorithm. The secretary algorithm has been well studied, so it's unlikely that it can be improved, at least for this problem, this setting. But the knapsack algorithm, I think, has a bit, possibly some room for improvement, especially for small items, because we didn't make any assumption of, say, if the item is small, then the knapsack, intuitively, it's harder to get filled up quickly. In a previous paper, they were using this assumption, in Babayov et al. But then when it comes to large items, they would do worse. So eventually their competitive ratio was worse. Maybe there is some room for improvement. For example, we applied Markov's. I don't know if one can model a bit the random experiment differently, maybe even Chernoff or some other bounds could be applied. So I see that as probably the main direction. Otherwise, we saw that with probability C over D, the knapsack algorithm starts with an empty knapsack, but maybe that can be tightened. So it could be that if the first item is not of size 1, then we could have space for more items, or we could start with an knapsack that is not completely full. Or also other approaches to interleave these two. Okay, finally, this problem attracted some interest also because as some applications like vehicle charging, electrical vehicle charging, which is becoming very relevant these days. So possibly some other settings and some other motivation. I have seen it being studied machine learning advice, and they did some work there. It seemed pretty interesting. I haven't looked so much into it, but it's another direction. Okay. Wish to thank you all for your attention. Happy to take any questions, discuss any ideas.
Like one question, so what are the other beyond worst case models?
Right. I've seen them. The setting where you augment the algorithm with predictions. I have seen also some other models. I can get back to you with some references. Do you have in mind some other models?
Okay.
Okay.
So algorithms with predictions make sense.
Does something like this also like maybe have something for the integrals and setting as well, or is it
Right.
just for the?
Essentially, what you see up to here, up to here works for the integral setting, with the only difference that instead of packing this XIL, you pack integrally with probability.
With probability.
Yeah, and then more or less the same analysis goes through. You just lose a little bit in the competitive ratio, and basically that is how they achieved this 6.65 that is here. Yeah, the one at the bottom right. Yep.
Got it.
Good. Any other questions?
Yeah. Do they also like combine with the secretary algorithm?
Yes, they do. In some sense, their algorithm here, or at least their analysis, has a worse competitive ratio because you don't have these, all these intervals. So eventually, for the secretary algorithm, they actually consider, not only one item, but up to k, where I think k is 3. So they considered all the ways which you can fact 3 items. So you get a bit better. But the problem with that is that in our case, you could consider 3, but it doesn't help in the analysis because the number of items in the solution can be big. And this case secretary algorithm, what they give you vanishes as k grows. So for 3, okay, you get something, but then you don't get anything for the final competitive ratio. Yeah, but they have a paper on case secretary algorithm. I think for one secretary is well understood. Well, they are really, it's not clear how good you can do. Because you can go beyond the E. Using also other approaches than the one we saw. Yes, if you like the problem, happy to talk about it and see if there are ways to improve it. Okay, thanks a lot again.